Hi everyone, welcome to the Tech Talk of Demcon, compliant mechanism under high current. The next 20 minutes you're going to listen to Casper van Dijke and Sietze Oostveen. We're going to tell you more about this challenging project. After that there's a live Q&A where you can ask all your questions. And afterwards you can go to Wonder Me, where you can talk even more about the project if you like. Alright, so you find the links in the description below. Thank you for watching and enjoy the Tech Talk.
So welcome everyone to today's Tech Talk, where Sietze and I will give an insight on the projects we do within Demcon, which are often multidisciplinary, where different disciplines from mechanical to electrical to software have to work together to get the right solution for the customer. In this case, a compliant mechanism under high current. So one of our customers had a question regarding a component exposed to a very high volumetric heat load in the range of 50 kilowatts on a component the size of a straw, so pretty small, which they cool with liquid metal. The resulting stresses inside the material are that high that it's reaching the boundaries of the material, and to make sure that the component actually survives this volumetric heat load, we need to do some tests to make sure it does. We like doing tests at Demcon because it always is an opportunity to break stuff. So therefore we designed with our team a setup that could simulate the actual heat loads on a similar kind of component. We couldn't do that with the same equipment, so we had to think of alternative strategies to put it on the heat load. We've thought of inductive power, infrared, even a blowtorch was thought about, but in the end we went for Joule heating because it gave the most representative heat load in the end. If I look a bit wider to the content of the presentation, so we want to discuss first something about applying the actual heat load, the actual current, the Joule heating, and on the other side connecting the actual current. First part will be done by Sietze, and I will pick up on the next part.
So over here we have a schematic of the test setup. There is the liquid metal loop, which is highlighted right now, but this won't be the focus of today's presentation. Instead we'll be looking deeply at the current supply, and this, like Casper said, we are using this to simulate the heat load. In order to do so we need 15 kiloamperes of current. Now 15 kiloamperes is a very big number, so to put that a little bit into perspective, if we put this same current on a regular copper wire, like a meter long standard diameter used for everyday applications, this wire would melt within 30 nanoseconds. So this heat load is very large, and that's why we also need to design very carefully. For example, right here we have a picture of the current setup. So on the right is the power supply connected with big copper cables to the test setup. And you can see a banana for scale. Now the surface area of these cables is about 2000 square millimeters, and therefore the resistance of these cables is only about a micro ohm. Furthermore, you can see these cables are water cooled, and some silver connections are attached. That is because the contact resistance of two copper parts attached to each other is actually so high, or like higher, that we needed to be careful for the heat generation on these contacts, and therefore silver plating some components was the solution. There are some further risks and complications involved with applying this high current. For example, if we take a look at the liquid metal loop again, of course the shortest path is straight through the test section, but because the liquid metal is very well conductive, we have this long path which the electricity can also take, and therefore that path will also generate heat in the liquid metal, which could be a risk for the test setup. Fortunately, we estimate that the heat generated by this short circuit is manageable. So some further risks and complications involve, for example, clamping the copper onto the tubing. Now, when copper reaches a higher temperature and approaches the melting temperature, it actually starts to creep away from the force. Thus, if this copper gets too hot, we will simply the mechanism from clamping will stop working, which is a risk in our test setup. In addition, when copper heats up, the electrical resistance increases, and therefore, because we apply such a huge current, the heat generated in this copper also increases in turn, and that keeps going in a cycle. The solution, of course, is to instead of keeping a constant current, we run the power supply voltage controlled. And a last little issue is if current flows through the liquid metal in the setup, this actually creates a pinching effect because of the Lorentz forces. Now, this pinching effect can create pressure gradients in your fluid, which can, for example, cause issues with cavitation and so on, which is very difficult to deal with and therefore difficult to design around. Now, I hope it's clear that it's very complicated to apply this current, but it's also a big challenge mechanically. So, Casper.
Thank you, Sietze. So you've seen some examples of the multidisciplinarity of the issue we're facing here. Now a bit more onto the mechanical side of the issue. So if you would basically connect the copper cables onto the test section straight up and have a non-compliant connection, then the expansion of the test section could not be reached, because basically the material around it is too heavy and fixed, that the actual tube test section would break. It would rupture, and because we only want to investigate the actual thermal gradients on the component and not the stresses because of the connection, we needed to design a fully compliant connection where we actually decouple the application of the power, application of the current from the actual component itself. We do it in two steps, a little bit more on the first step. So this is basically the connection from the top electrode to the power supply, and we have done some tests where Sietze can tell something more about.
So over here is a picture and a movie of a test we did with braided copper. So you can see the connections of the power supply linked together with the braided copper and some remaining copper cables. Now, this test was to confirm that this braided copper piece remains flexible even under a high current. So what you can see in the test is that we move it without the current, then we apply the large current on it, and you can see the black cables pinch together, which is the effect we're investigating. And fortunately, when we move it again once the current is applied, the braided copper stays flexible, and therefore the test is successful. And a little bit fun fact, we are measuring the temperatures on these black copper cables, and these heated up to about 100 degrees within 10 seconds. So the heat load is again very dangerous.
Thank you, Sietze. What this actually also shows is that you can build a really simple test setup where you can do some in-between measurements to see if your principle works in the way you think it should. So this is a very simple setup, just with wood and some cables to just do an intermediate test to see if the components you're thinking of actually work. Further to the test section itself, so we've talked about the U-bend shape here, the braided copper. Now we also need to talk about the expansion of the actual tube, the component. So this will expand and needs to be able to expand freely, because we only wanted to see the results of the stresses caused by the thermal gradient of the actual heat, and not the expansion of the tube. So again, this will be free in 1 degree. All other degrees need to be fixed, because there's a lot of weight on top of the top electrode, and we want to keep that from ruining our test basically, and ruining our tube. I'll go in a bit further on that. This is actually the real size of the test section itself. So here is again the part of the straw we were talking about. It's connected to two copper rings which are connected to the electrode. Before I go into that a little bit further on the connection, because of the high current and currents likes to flow through low resistive parts, copper is okay, but the test section itself is pretty high in resistance, so the current tends to flow and step over to the next component really close to the tube, which causes very high current densities at that location, which is also again tricky for the material because the temperatures tend to get very high. What we've done there is we've actually soldered the two pieces with gold soldering to make sure that there's a durable connection which is actually also ductile at high temperatures and also remains there at these high temperatures. Silver, for instance, wouldn't work because it will diffuse into the copper. So again, an example of how a mechanical problem is not only mechanical but also has different connections to other disciplines. Zoomed out a bit further, you can actually see the top and the bottom electrode, which are clamped on the two copper rings on the test section, using these clamping brackets. There's also heaters inside the electrodes because we're cooling with liquid metal, and that's only liquid at 150 degrees Celsius. So we need to heat up the whole thing first to make sure the cooling actually works before we can start with applying the current. One thing to mention as well is that you can see some leaf springs on top and the bottom. Those are actually parts to keep the connection from the test section to the rest of the tubing stable. You don't want to break your test section if you mount the cable, or the tubing. If we zoom out even a bit further, then you will see the full setup, where you can still see the top and bottom electrodes, but now there's a top and a bottom crown put in between, which are actually connected with some leaf springs. So the top crown is connected to the top electrode, and the bottom crown is connected to the bottom electrode. And in between these two crowns, which are actually like two tripods in between each other, there's leaf springs which actually provide the necessary compliance we actually need. I have some analysis on that which I can show. So these are FEM images with displacements by applying certain force. So we've applied 10 newtons in all directions and a torque of 10 newton meters in all rotations. What you can actually see very well here is that the displacement in height direction is quite large if you compare to the displacement in X and Y direction, X and Z direction, sorry. And also the torques applied are pretty high, and deformation is very low, which is what we actually want. If I run the simulation, you can actually see the top electrode moving upward with minimal force, only 10 newtons in this case. And that was at the end our objective, to have a compliancy in one direction and fixing in all other directions. So there was a lot of work and a lot of people working together to achieve all this. And this is the result in 3D, where we have let's say the expectation we have up front, and on the right the actual result of the manufactured part, which is in our lab here. You can see the braided copper parts, connection to the top electrode, part of the leaf spring in between, the bottom electrode with the connections to the heaters, and the actual leaf springs in between, which show you that by doing all these steps and doing all designs, making all the analysis, finding all the issues, you can actually make something which should be able to work at the end. Thank you for your attention.
Thank you. Okay, so welcome back. If you want to ask any questions, you can join us at Slido and enter this code, and we'll get to see your questions.
Maybe nice to have a little start. So you're probably wondering why we have chosen for this specific setup of leaf springs and expansion. When we started the project, we first used as a concept bent leaf springs, so bent flat leaf springs, 3 of them on the top and 3 of them on the bottom, to clamp the 2 separate parts together. But eventually we ended up with a space issue where we could not fit all the material inside our volume, let's say, and also had some issues with the heat being too close to the leaf spring. So we had to redesign and finally get the leaf springs on the outside, further to the outside, further away from the tube to get rid of the heat, and give us the same kind of functionality basically, which turned out to be work out really well. So awaiting further questions, I'll give. There's the first question. Okay, so thank you, Anonymous, for the question. So how does the Joule heating relate to the actual final heat load? So basically 100% accurate, basically. So we can get the same levels of heat inside our component, the same peak levels, same average levels, also in the same area. So for us this was a really good a good reference load to get on the piece, to make sure we actually do the right kind of test and have the right kind of results with our component, to see if it would match, if it would keep up and stay a whole in the final concept. That's a very good question, actually. Maybe Sietze can say something about that.
Yeah, so the current state of the test, right now we're in the implementation phase in the lab. So a lot of the components we showed you are together, and we are testing the first functionalities, including the heaters we mentioned, including the power supply. But we're not yet at testing the whole system as together.
Yeah. And maybe nice to tell that also the initial, let's say, test runs with the current have also been done. So we're not going max on right away. So we tested with let's say 10% current, which means a 1% actual heat load, but still a reasonable 1300 amps we put through the component. Okay, the next question is. No. So, question from Otte about the mechanism. So, these are not five wires, but they're actually 12 wire flexures. So, like I mentioned, we have the 2 crowns sticking into each other, and basically bottom and top of the crowns are connected at every step from one crown to another. So, in total, we have about 12 of these wire flexures. If you look at it in the, let's say, in a pure way, it's a bit overdetermined, the construction. But what you actually see is that because the crowns are that long, that the tips of the crown also bend in a bit and give you the flexibility of actually moving in and out with the total setup. So the expansion also gives you a bit of a bending of the tips of the crowns as well. Sietze, maybe you can say something about that.
Right, so next question is about the Lorentz force caused by the huge current. So for most of the metal parts in the setup, it actually doesn't have that high of an impact. We did several calculations and also a test with the U-bend, as you saw. On those, we don't think it will be an issue. However, in the liquid metal, it still is a risk because it's very difficult to simulate or estimate what kind of pressure drop we can expect from these forces. Yeah, that is still a risk, and we've taken some measures, of course, to prevent this being an issue. But yeah, especially in the liquid metal, we still think this is a risk.
And what we can still do to see if it occurs, if the cavitation occurs, is put a microphone close by and see how the sound changes when we apply the high current, to see if there are some changes in sound, also if there's some changes in pressure drop or flow rate. Something we can do to check for that.
So the next question is what type of power supply is used to generate 15 kiloampere? So surprisingly, this is a rather standard component. When we were looking into all the options to use, it actually happens to be that in the power industry, the high power electrics, components like these are actually made more often than you would think. So we didn't actually have to go all out with a supplier and design something entirely new. Yeah. Yeah, I believe it's just standard.
Yeah. What is good to mention is that you also need to connect it to the power grid in the building, and for that we had to change a transformer we have outside the building. We had to increase the power supply for let's say the whole company locally, and there's two these size, let's say wrist size cables running inside the building to power our full setup. So that needs to be taken into account, but other than that, it's a normal power supply. Okay, so question by Koen, compliancy in the electric system and with the copper wire, with the braided copper wire, but also is there a compliance required in the fluid cooling system? Of course there is. Also there you have expanding pieces and small movements. The thing is the regular tubing is let's say standard Swayslock tubing, which is rather, let's say has a rather thick wall, but still if you have sufficient length is rather flexible. So that's basically how we use that compliance. So we have enough length, enough bends, let's say, to overcome this issue.
So a question from Mark: how many amps run through the liquid metal loop? Our estimation is that from this 15 kiloamps, roughly 500 amp will run through from the liquid metal the long way around. Which is of course a loss from the power supply, but yeah, so it's about 500 ampere.
Okay, so thank you for your questions. If you want to know more about the setup and discuss this further, you can join on WonderMe, where we have a network session, and I hope to see you there as well. Thank you for your attention.
Thank you.